Hi, everybody. I hope you all are doing well, had a nice weekend. Welcome to lecture number 8 for industrialized construction, titled Mass Customization Using Kit of Parts and Digital Design Platforms. So let's jump right into it. We have a full day, including a guest presentation during the first half of the lecture, and in the second half of the lecture, we'll have a guest lecture by the company Project Frog. So as always, if you have questions, please feel free to put them into the chat or let me know if there are any technical difficulties or anything like that. Otherwise, we're going to jump right into it. So as a reminder, we've been talking about this framework for industrialized construction that was introduced 2 weeks ago. And I like to be able to show for each lecture which of these areas we're talking about. So today's class, I really think, falls underneath 3 specific areas of this framework. And you can keep this in mind for your own projects as you start to think about how do you think about each of these areas and assigning points for your own course project. So what we're talking about today with mass customization and kit of parts falls at the intersection of 3 different areas. So the first is the prefabrication of parts. I think that's pretty clear. We'll be talking about how you develop a kit of parts strategy, but it also really connects to this use of information communication technology and tools such as digital design platforms. And it's all made possible by having long-term relationships in the supply chain so that you are able to integrate that information together. So that's just an overview of kind of how it connects. And if you remember last class, we talked about the idea of platforms in industrialized construction. And I introduced the idea here that we do have information that transfers from design and customer acquisition to configuration engineering to manufacturing, production, and assembly and logistics. But what the real interesting opportunity is for platforms in industrialized construction is to be able to transfer that information upstream. So you can go from assembly and logistics and embed that information into the rules as rules and restraints earlier in the process. And we're going to talk a lot more about what that might mean or what that might practically look like in today's class. And then the second thing I'll remind you from last week is that we talked about the difference between projects, processes, and platforms. And here are just 3 very quick representations, right? So you have a project, which is a specific period of time where you are working to complete a certain set of activities. So design and planning all the way through site work and the completion of the building. Then you have a process, which is the steps that you follow in developing your platform. So we talked about a technical platform process. And I mentioned, if you recall, there's one part of the process that could be considered kind of the digital configuration or integration. And then finally, you have the product platform, which is the rules and the technical system. Maybe, for example, the rules of the Lego system would be an example of the product platform. So today we're going to be talking about this kind of integration of the digital platform as one step of the process with the rules that might exist within the product platforms. And one way that you can do this is through the use of something called the configurator. We'll talk about that in more detail. But that's a review of last class and where we are today. So today I want to start by talking about how different approaches to industrialization have different types of platforms, different types of systems, and different products that come from that. And here is a really helpful diagram that I think helps explain the different product approaches which can be used in different ways within industrialized construction. So for example, let me first explain how the diagram works. If you go from left to right, from 0 to 100%, this represents the degree of finished product specifications. So how specific are the exact specifications about the product that are going to be made? And here across this diagonal is the design entry point for customization. So as you move over towards this direction, you have a more finished product, but you have less opportunities for customization. And this is a really helpful way of understanding the differences in which the way things are structured. So I'll talk about each of the 4 categories in a moment, but another way to think about it is as you kind of go in this direction, as you go higher, you have more flexibility. So this means you have low platform development. You haven't invested in a very specific platform, but you've invested more in the flexibility side of things. So you can basically build anything you want. And if you go on the right side, as you go towards more higher level finished product specifications, you have more predictability. So you have a more developed platform and you can predict the processes, you can predict the final product, and you can predict the price more specifically. And then within those two different categories, there's many different approaches that you might wish to use for industrialized construction. And let me just give some specific examples to make it quite clear. So at the highest level, with the most amount of flexibility and the least amount of predictability, is the process of engineer to order. And the way that we have specified products in engineer to order systems, the traditional system that we use today, is the use of norms and standards. We have a building code, we have norms about how construction happens, and then therefore those norms and standards inform the engineering process every time, and it can be highly customized, highly flexible. The problem, as we've talked about in this class, is that it's less predictable. So we don't have a lot of prediction because we don't have very strong product specifications. The next step down is the idea of kind of a generic platform or platform engineering, where you are developing a technical building system or a prefabricated building system that still has a lot of flexibility, but it doesn't necessarily have specific rules that it has to pertain to. And so I used two examples. Arne, who unfortunately we weren't able to visit their factory, but we will have a guest lecture by them in 3 weeks. And also the guest lecture by Daiwa House, I think, gave good examples of how you can have a building system that you've developed some ideas behind, and they have some more predictability, but still can be applied in many different ways. Next, you have the idea of mass customization using a kit of parts. And this is the idea that you create a product platform for the entire building system. And then the customization point is really a configuration engineering process. We're going to say a lot more about that because that's the topic today. But the two examples we've used in the case studies was first Katerra, and the second one, which we'll hear from in the second half of the lecture, is from Project Frog. These are two companies that use different business models. Katerra is vertically integrated. Project Frog is more of a digital systems integration, but they still use the same approach to platform predefinition, which is to define a specific kit of parts and then engage in configuration engineering. And then finally, you have at the most defined product specifications, the idea of finished module families. This means that you fully design and specify a module. It could be a volumetric element, but it's completely defined for you. And then the customer can select which of those modules they would like to pick. So that's why it's called select variant, which basically means you can pick the final product, and there might be some variation in the different products you can pick, but the product is not going to be customized and tailored to your individual solution. And the example we'll see in a couple of weeks also with a guest lecture will be from Bokluk, which is the joint venture of Skanska and IKEA, who have been very successful with the select variant approach. I don't want to argue that one of these is better than the other. They all have strengths and weaknesses to these approaches. But instead, I just want to point out that there are different approaches to how the platform is operationalized. And it matters about how much customization you wish to provide within the platform. Today, we're going to focus in only on one of these, and that's the idea of mass customization using a kit of parts. And we're going to go into much greater detail here. I think this is an approach that has a lot of potential moving forward because it has a very nice balance between flexibility and also within predictability. So I think that we will see more of these approaches moving forward. Okay, but let's start from the beginning. And this is an idea that hopefully you also got from your assignment and your reading. It's the idea of mass customization. And so I wanted to begin by just summarizing what is mass customization. And I think this quote is probably the most simple, but gets the point across. It's producing goods and services to meet individual customers' need with near mass production efficiency. So you still have customization, but it's done with a kind of large scale or mass approach. And you're never going to get exactly the same efficiencies as mass production, but you can get close to it. That's a bit of an academic definition or maybe a bit dry. So here I have a diagram that I found that I think highlights the process of mass customization in a nice way. So first we start down here, you see you have a manufacturing portfolio, and these are all kind of the different things that you could possibly manufacture. You know how to manufacture these circles, these dots. And then you have a customer, and the customer has to engage with a choice navigation tool. So this could be like a configurator or something similar. And then the configurator helps them move through the solution space. It helps guide them through the different possible choices that they can make until they make a design decision. And that design decision enables manufacturing to proceed. And in the meantime, each of these decisions is passed and translated into manufacturing language, so it can meet the language of the supply chain. So the supply chain can then fabricate the different design decisions. And then you've now created a customer order that's mass customized, but also matches the manufacturing requirements. And this can be moved into the production and assembly processes, which can then be delivered to the final customer. So that's a very graphic representation of what mass customization journey might look like for a customer. It's going to be more complex in industrialized construction, but at a simple view, this is what's happening. But it's important to note that users need good design tools for mass customization. And I wanted to use a very practical example to describe how the use of design tools like a configurator can be very helpful, but also can be a challenge for customers to use in their delivery of, or for their purchasing of products that use mass customization. So when I moved to Switzerland 2 years ago, one of the first things you have to do in setting up your apartment is you have to go and get your wardrobe set up. So we went, of course, to IKEA, being a global brand, we were familiar with it. And we walked into the IKEA store and we looked at all the different options. There were some great options. And we realized that, oh, this will be perfect because we can configure our wardrobe to be exactly how we want it. And we can actually pick up that configured wardrobe on our way out of the store at IKEA today. You could either do this online right now, or you can go in the store. They have these tools, these computer stations that you can work with. So I went there, I loaded up the space, and then here we have this wardrobe planner, right? So you have a visualization of the space. You can kind of see what the wardrobe looks like. You have the different sizes and dimensions, and then you start picking out the pieces that you like. Now, in the end, then you kind of make all of these different decisions. My experience was not necessarily a positive one. I like IKEA a lot, but I had to deal with my 3-year-old son also kind of wanting my attention at the same time. And the number of choices that I had to make was a huge amount, because I could customize this any possible way that I wanted. And that can be a little bit overwhelming. So there were some feelings of kind of, oh, I need to have more engagement than if I bought a select variant product. If I just buy one wardrobe and I can't customize it, maybe I'm not 100% happy, but at least it's not taking a lot of my own time. At the same time, it was really fun and to be able to have this approach. And there were 2 areas that I think are particularly useful about this kind of configuration tool. The first is immediate visualization. So I'm able to see my product in real time and understand exactly what I'm getting. So there's a real-time visualization tool. And at the other time, there's a real-time cost feedback. So I understand my decisions, and I understand if I decide to put in a nice glass shelf, what that means for my overall cost. So this design tool gave me both visualization and cost information. And that's, I think, a helpful way of understanding what a configurator can provide for a customer. In summary, mass customization is meant to be a customer-friendly navigation tool where choices are displayed and can be selected from. It's a design tool that can translate design decisions directly into manufacturing language. And it provides production and assembly processes that are flexible enough to produce a diverse range of products. So this is the very short summary of mass customization. And now I wanted to move in and make sure we also had some engagement. So I wanted to send you into your breakout rooms. I will assign them in a moment. But the idea is that I want you to answer the question about how do you think that mass customization is different from traditional construction? And you can use some of the insights you had from your reading and reflection response, as well as some of the things I've said so far. I'll remind you that we have our class Jamboard at bit.ly /ICJam. So you can go there and I've set up a page. So just like last time, feel free to put in your post-it notes on the answers there and see what others write. And I'm about to start the breakout rooms now, and then we'll come back together in about 5 minutes. All right, well, some people are still joining us. I think they're putting in their last ideas. But I'll just kind of talk through for those that are already in the rooms. I think you can see my screen. So we have a couple of great examples of, I think, really good responses here, talking about how it's easier to use platforms. You have more interaction between the user, customer, and the manufacturer. I think that matches here with this idea that you have a more customer-friendly and customer-oriented process. Again, talking about the customer and involving them in the design process. Yeah, and then we have a lot about thinking about the predefined set of rules or the framework and how you can, it enables the information to be transferred quickly into the BIM data. For those of you that are just joining, I was just talking through some of the responses for those that had joined back earlier. I think everyone should be back now. And with that, so now we want to go a little bit deeper into the theory behind mass customization for industrialized construction. And so for that, we'll have a short lecture by Jianpeng Cao, who goes by Kemp as well. He'll be giving a short view into some of his research and how he's looking at configurators and kits of parts in his research. So Kemp, if you want to grab control of the screen sharing.
Hi, Daniel.
Hi, Kemp.
Hi, Dan. Can you hear me?
Yes.
Okay. So I will share my screen.
Perfect.
Now. Okay. Can you see my screen? Can you see my screen?
Not yet.
No? Hmm?
Hold on. But it might be on my fault here.
Yeah, I cannot start screen share while the other participating is sharing. I think you are sharing, so.
Let me stop here.
Okay.
Okay, you can grab it now.
Okay. Where is? Okay, share screen. Okay. Can you see my screen now?
Yes, perfect.
Okay, cool. So, and you can also hear me, right?
Yep.
Okay.
It's not on full screen though. It's just on the side.
Oh, okay. Yeah, I will make it. Okay. So how about now?
Perfect. Okay. All right, go for it.
Yeah. Hello everyone. I'm Jianpeng Cao, and you can also call me Camp. And let me just make this small. So I will skip this self-introduction because we don't have many time, so we don't have much time. And okay, so today my topic is about kit part-based configuration. And first, let's look at a conceptual framework of configurator, which I use it to represent the decision-making process. So first, you have this user input, like it can be from the experts and end customers, and you will know the difference between them, like the experts with knowledge and the end customer does not own the domain knowledge. And starting with the so besides then this is the main. Oh, where's my mouse? Oh, okay. So this is the main part of the configurators. It contains two pillars. One is the kit part library, and another is configuration rules. And basically, like the kit part library can be the 3D modules, 2D part and panels and the parts. I just give some examples here. And the configuration rules can be the building regulations, product composition strategy, and the production constraints. And here, I want to re-emphasize the importance of the reuse of knowledge. And this is quite lacking in our industry, as you can see. There's little connection from projects to projects. And you might already know the leasing framework of the IC, that big circle. And so I think you assume you understand the importance of continuous improvement. So, okay. And finally, the from configurator will pick up the appropriate kit or part from the library according to the rule set. In some sense, you can understand this is a decision support system. And if you look at the whole building design process, like this is just one step. And this can be a sequential, like you need to stack like step by step, and the diagram might be a little bit too detailed, and I don't want to illustrate a lot about this diagram, but it represents the same meaning as above, just following a predefined order, and the definition of the order it depends on your design problem. And if you are familiar with the Markov decision process, and you can think this is a little bit similar to that. Okay, so let's move to a little bit detailed stuff. So let's first look at the KitOpart library, which you can see the Kit Connect from Project Frog in more detail at the second part of the lecture. The structure of the library is hierarchical. So the super system, I call it the super system, and the subsystem. I know it might be a little bit confusing, but I will try to make it more clear. So the super system level is a spatial layout, which you can represent it as a graph structure stored in the database. So this is the presentation, like the visualization part, and this is the data structure behind it. So each node refers to a space, and the H represents the connection of the space. And once you want to add or delete a space, or you can just add a node and build the connection between the other nodes. And at the next level is a system level. So customer select, so for example, I select this pink space. I'm going to configure this pink space. I'm using the system library. The system library basically contains the structural components, like the panels, the modules, and you can like use it to separate your room and like determine your spatial, like the inner layout. And at the lowest level is a subsystem. The library is usually categorized by the element suppliers. For example, the openings, the ductings, the finishes, and the main material. Like for example, I use timber here. So usually those three libraries, if existed in the company, which is not usually the case. But we assume they already built the library, and but this library is located independently. So in other words, they are not only located physically independent, but also logically. Like the language they use is different, and the connection between them, there's no connection between them. So theoretically, how to build a connection between those libraries is a challenge. And we built it using this idea of object-oriented modeling strategy. So each item here can be modeled as an object with the attributes and methods. The idea is the methods include the information editing and extraction. The extracted attributes can be used to search for the components in the lowest level. But this search strategy, you have to figure like the interpretability problem, the semantic mismatching problem. But this is a little bit detail. And once you find the most fit element in your library, probably there's no fit element, but we can find the most like matched one. So you can define the metric, how you match the similarity between what you want and what exists in the library. And then you can manually edit the design manager parameters. And if there's a and once it fits your requirements, you can specify and add that element to the super element. And this also like need to formalize in your methods. So this is like a brief introduction about the hierarchy part of library and how you build a connection. And the next part is the configuration rules. So we need to think about how to formalize it using existing technique. And the current problem is that when you complete a design, the product structure does not explicitly contain rules for doing inference. And the structure also doesn't represent the actual assembly knowledge, which you can rethink the hierarchical relationship we talked about before. Besides, there are other more interesting constraints. So first, I want to say this is like the tree structure. and modeled in the authority using authority, and you can basically you can formalize it into this parent-child node relationship and to represent the hierarchical system. And you can define the attributes like, for example, the project has apartment, has balcony, and has module, and what kind of module you have. You can, so this is the beauty of ontology. So when you define a structure, like here in the left side, you can also encode some rules and attributes. And I will give you some examples. So for this simple modular building, apartment might include an entrance module, kitchen module, sleeping module. This is simple, but you need to ask system like automatically check whether when you build an apartment, whether it includes those modules. And for more complicated example, if I define for building with certain number of floors and how many modules has to be stacked horizontally on a certain plan to resist the horizontal nodes, and the system need to first know what type of module here and do the aggregation itself and check whether the number of the total modules on the certain floor plan match the regulations. Okay, and the last is another kind of dependency constraint, which basically you select, it's very easy to understand, right? Like when you select one of the element, probably you have to select the adjacent. The adjacent element has also be partially defined. And in the end, I want to talk about the manufacturing constraint. This is an important and often neglected aspect by designers. So when there's a kit part, for example, a panel here, and including its components like sheathing, start, blocking, and how do you know whether it can be manufactured or by the available machines, and or more deeply knowing how long it takes, how accurate or precise the manufactured part is according to your design. So to solve this problem, we need to introduce a concept called the feature-based modeling, and the workflow can be simplified as given a kit part. The first step is to build the geometry representation, and depends on what tool you use. It might be 2D or 3D, parameter-based or just pixel-based. Then there's a feature table, which basically tells you the geometry the machine can finish, as simple as a hole, a snot, what's this? Or this a different shape of snot. And so then the configurator need to detect those features, no matter manually or automatically. The feature detecting similar to what you hear about the face recognition, and based on the extracted feature, the most appropriate machine can be selected. Then a production line can be arranged according to the operational sequence. So in a word, a manufacturable design is validated by a feasible operation sequence and implemented by the available machine tools. So I think what time is it? I think this is what I'm going to present now, and I will give back to Daniel. And if you have any questions, so all this is about my research. I'm very open and welcome to your questions and make me improve my research. Thank you.
Thanks so much, Kemp, for the great presentation. And if you have questions, feel free to put them into the chat, and I'll try to finish up in about 5 minutes. And then Kemp and I will both be available to answer some questions. So feel free to write your questions in the chat, and we'll have about 5 minutes at the end. So I just want to wrap up this lecture with 5 more minutes talking about what this kind of overall digital platform enables in terms of Industry 4.0. So, Industry 4.0, if you haven't heard of it, I'd be surprised. Everyone's talking about it. It has a lot of different definitions, but for this sense, I just want to talk about the advantage of this kind of cyber-physical interconnection, or the idea that our hardware and software platforms can be linked together in the process. And so we've talked about how to create a physical platform. And now today we're talking about how a digital software platform can help configure that digital hardware platform, or make better use of that hardware. And the example I like to use is that of the iPhone. Again, I use the iPhone a lot in this class. But if you think about just the iPhone being developed as a piece of hardware, you know, Steve Jobs infamously said in 2008, I believe it was, that you know, we'll make the iPhone and people will access information through our browser-based you know, Safari app. And so basically anybody who wants to get information from the internet has to use Safari. And then the iPhone was released and people liked it, but it didn't have this huge following that we have today. Because it took about 6 months before Apple decided to implement their software platform, which I would describe as the App Store. So now all of a sudden they enabled a new ecosystem where they had hardware connected to a software development platform, and they had the ability for multiple developers to create their own apps on top of that hardware platform. And that's kind of getting into all this ecosystem stuff that I don't need to worry about, but instead it's this interplay between hardware and software that I want you to take away, is that that's what this kind of configuration platform really enables. There's a couple examples just that I want to briefly show. This is BuildX, which you know, they developed a very low resolution kind of idea of how, if this was a CNC platform, it would tell you how your CNC costs for fabrication would change as you change the geometry. And I thought this was a nice example of their product called BuildX, and Open Systems Lab does a lot on open source, open systems. So I wanted to highlight their really interesting work. Then you have examples like Place Technologies in Sydney, where you can basically, you know, walk through the space and start configuring. In this case, the video shows furniture, but you can configure like kitchens and things like this. And these are kind of low resolution examples of this hardware and software platforms being put together. I think perhaps one of the most interesting examples that have recently come out is the development of a precision manufactured housing digital toolkit between the City of London, Bryden Wood, and CAS Consultancy. And so this was this full digital systems integration suite that enables someone to start from scratch and basically configure a modular building construction in the City of London, so in a specific location. And I don't have time, I think, to show the whole video. Let me just jump ahead. So here's kind of the configuration process, right? So you start to design your project. You load the map so you can understand where your site is. You want to draw the boundary of the site so you kind of know your site, and you just delete the existing buildings. And then you can go in and add kind of the footprint of the building, so you understand what the building might look like and the number of floors, the height of the building. And then you can start to also go into the mix design. So over here you have kind of like the mix design. So you're understanding how the mix changes, and then using the rules that Kemp talked about. As you change the floor plan design, that mix design should automatically update. So then you can start adjust the area by type, start thinking about all these different things. And then downstream, you can start to think about how it connects to manufacturing. Just for the sake of time, I'm gonna skip forward. I think this is their example of panelized facade. So you can get the exact precise sizes of the panel facade, but this can even go much further in the future. So this is just a very brief example of you know, kind of how these things are emerging. Let's see if I can skip ahead to the next. There we go. And I will just summarize it like this. The platforms change the design process. I apologize for the low resolution. But in the traditional design process, you see here on the x-axis the percentage of common parts, and then on the y-axis the degree of flexibility. So in traditional design, you have very few common parts, and you have lots of flexibility, and you have lots of unique parts. So this is very good for flexibility, but again, not so good for prediction of the performance. And then when we go to a product platform with configuration, you start to have many fewer unique parts, maybe even 0 unique parts, but instead you have many common parts and different modules or variations. So it changes the design process. And the idea of configurators are that they are design tools to help navigate this new design process. I'm going to skip over this one, but I just want to say that configurators also require the role of new positions, like someone that is in charge of the configuration design, and they design the configuration process. But I'm not going to spend too much time on this slide. Instead, I want to just kind of summarize here with this diagram, which I think is a very futuristic view of construction that I have many agreements with. And this is the idea, it came out in 2016 about this is what the future of construction projects will look like. You begin here with the decision that you want to have a new or a changed asset. And so you would go into design development in using a tool like BIM. This is how we have it today. But in the future, we're going to see projects that start engaging with this idea of mass customization and have intelligent interactions with the manufacturing Industry 4.0 supply chain, which can be optimized. And then what we've talked about in this lecture is the idea that you would have optimized configuration rules that flow back into the design and development of the project. So you have this feedback loop we've been talking about. And then you might connect that with the assembly processes, of course, that you need to have that connected. And furthermore, once you've assembled the project, you start to create intelligent assets. This is the idea of digital twins that you can maintain and upgrade and replace. And furthermore, then you have the chance for kind of performance feedback and analytics. So now you have this loop from how the items perform back into manufacturing. And you have the opportunity for circular economy because now you can use these intelligent assets, understand where they are in the building. And when you're done with that building's life cycle, you can then go back to reuse, redistribute, remanufacture, or if necessary, recycle the building. So this is, in my mind, a very nice futuristic vision of the future of construction. And I think it all starts with this kind of core configuration engine that we've talked about today in class. All right, I'm going to end here with my little brief before our guest lecture. This is some nice theory and some nice examples that we started with in today's lecture, but I think there's still a question: how do we create this kit of parts? How do we create these configuration rules? It's great from an academic perspective, but how can industry create these rules and these parts? And that's going to be exactly what our guest lecture will be from Project Frog after the break. So we will have a short break now, and for maybe the first 5 minutes or so, Kemp and I are happy to answer some questions. And then at 3:45, we'll have our guest lecture from Mike Eggers of Project Frog. So I will see if I can pull up the chat. I don't see any questions yet, but please feel free, put some questions into the chats, and otherwise we'll be back at 3:45.